In this screencast, I'm going to show you an example of how to compute Coulomb's law at a point of interest P, the E field at a point of interest P, due to a line charge. Before I get going, though, I want to show you some steps that I think are useful to apply to all of Coulomb's law problems, whether it's a line charge, a surface charge, or a volume charge. Step 1, and it's going to be impossible if you don't follow step 1, would be to draw a picture. Or if you're not going to draw a picture, at least have the computer draw a picture. Step 2, determine the formula that you're going to use, the specific form. In our case, this will be the line charge formula. Step 3, and you might do step 3 before step 2, would be to determine the symmetry of the problem. This is going to dictate what coordinate system we're going to use, Cartesian, spherical, or cylindrical. Step 4, will be to determine the R script vector and magnitude. Step 5, and this might sound abstract right now, but it will be to convert any unit vectors into Cartesian. And this will be as needed. You'll see whether you need it or not depending on the problem. So it could be that if you have spherical or cylindrical symmetry, you might have a problem that's set up and it has unit vectors that are r hat or s hat. Those depend on theta and phi, which you'll be integrating over. And if you fail to do this, you're going to miss part of the function that you're integrating. Step 6 will be basically to integrate and solve the problem. And I'm out of room on my screen here. I won't put it down, write it down. But if there's a step 7, it would be to make sure that your answer makes sense, right? So you can use a lot of common sense to figure out whether the answer you come up with matches what you might predict before doing the problem. Okay, let's move on to an actual example of line charge. This is an example 2.2 on page 64 of Griffiths. And what we're interested in here is the electric field at point P due to the line charge that you see below. The line charge is this dark green line with the white border. So if we're following our steps, our first step is to draw a picture. The picture is here. Something we also know about this problem that's given this problem is that the line density lambda is constant. I'm just going to write that in the corner. That's going to be helpful. That'll simplify our problem. Lambda equals constant. It won't always be constant. That's when the book's being nice to you. Okay. And now our next step is to find the formula for Coulomb's law at this point, and that's just our line charge formula, the electric field at point P. So r vector there that I drew, it's a function of r vector, is from the origin to point P. That's going to be equal to r1 over 4 pi e naught, always comes with the integral of the line density, which could be a function of r prime. It's not in this case, which is nice, but let's leave it general, over script r squared. We need to keep track of the unit vector direction for all these bits of line charge and integrate it over the line charge element dl. Prime again shows that the integral is over the charge distribution. Okay, on to step 3. Step 3 is what is the symmetry of the problem. And this one could either be cylindrical or Cartesian. When you have an infinitesimal line of charge, I mean that line is an infinitesimally, it's infinitely thin. You know, is it an infinitely thin cylinder or line? In my opinion, actually, a cylinder kind of makes more sense. I think of a wire, and I shrink that wire down. But again, it's a one-dimensional wire, so Cartesian works. Your book does Cartesian. It's easy, so let's go with Cartesian. So following the example from Griffiths, we're going to label this the z-axis, and we're going to label this the x-axis. Let me erase that, make that a little bit clearer. Okay. Step 4 is to find our script vector. And let's write the definition of our script vector, and we'll try to use our colors again to make it a little clearer. Again, this is, in some ways, this is the essence of the problem. This is where you'll go wrong. This is where not being careful with the notation is going to screw things up. Alright, so our script vector, once again, it's going to be equal to, we used blue last time for the vector from the origin to the point, and then we used red minus the prime vector. So let's draw, we might as well draw our blue vector first. That goes from the origin to the point where we're interested in calculating the field. So, alright, so from the origin to the field point P. That's our blue vector. How about our red prime vector? This is, by definition, from the origin to the charge distribution. And what we're going to do is we're going to go to infinitesimal element, a generic infinitesimal element on that charge distribution. The integral is going to add those up then each one at a time, as if we had an infinite amount of point charges along this, or charge elements along here. Okay? So we need to just draw a generic charge element, line element. I'm going to do that right here. Just make a blob. And that's charge element DL. Alright, let's see if we can squeeze this in here. We're going to have, it's going to be a little bit crowded. There we go. So our R prime then is going to be from the origin to that source. There we go, had a little problem drawing that there. There's our R prime. Alright, so we have R prime, and we didn't label our R. This one was just regular R. And then our script is going to be from that source point to the field point. Let's erase that. That didn't quite work. Try that again. Cool, that's more like it. That's going to be our R script vector. Okay. Now what we need to do is we need to be a little more specific with that R script vector. So what we're going to do is we're going to define lengths of these and directions. We're going to actually get that R script into more detail. All right, let's call the, again, this will be a variable now of integration, as you'll find out, the R prime. Let's just give this a length of x prime. Alright, and then likewise, let's give the length of the vector from the origin to the field point. Let's give that a z. Note that's not z prime, that's just z. Okay. Now what we need to do is find out what R, the blue, just regular R vector or an R prime vector. Let's get the equation. Let's see if we can make that smaller. Get this one out of the way. Oh, it's all attached. Not a problem. Let's go to the next slide, and we'll copy some of this over. We left off trying to define the R and R prime vector more specifically in the coordinate system using the lengths of the vectors drawn on the diagram. So let's start with the position vector R. Looking at the figure below, or a little bit to the side and below, that's just going to be z hat. Likewise, let's erase that a little bit. That's looking a little bit sloppy. There we go. That looks a little better. Likewise, the R prime vector is going to be equal to x prime x hat. And therefore, our generic script vector is going to be equal to z hat minus x prime x hat. Now something else that we're going to want is the magnitude of that vector. So the magnitude of that vector we're just going to call r. That's part of our equation. You can see I rewrote the equation down here, right? We're going to need that, the magnitude of r, and the r vector is going to, the r hat script vector is also going to need to use the magnitude of r as well. So that one is just squaring the components of the vector, as you've done many, many times before. So what we're going to get is and then taking the square root. This is just going to be square root of z squared plus x prime squared. See if I can get that root to continue. You can see there are some growing pains with this this software here. I can't always get my stylus right where I want it. All right, let's try make a prettier root there, and then we'll move on. A little bit better. All right, so unit vector r hat then, right, it's just going to be z hat minus x prime x hat divided by z squared plus x prime squared. Great, we're getting a lot warmer. So step 5 would be to convert the unit vectors into Cartesian, and then we're already there. Our unit vectors, we'll see, we're going to put this all into we're going to start putting all of this now, all that we have, into our integral here. And you can see that the unit vectors that are going to be part of this integral are already in Cartesian. So we are set. Let's plug this into the integral, plug this into the equation, and set it up, and that'll be the problem. Okay, let's start putting this all together. I've copied some of the information from the other screen, and we'll bring the figure back up again. So let me show you a little trick. Again, this is what we defined as our R script vectors and the length of the R script vector, and here's the generic formula for the R hat vector. It's just R script vector divided by the magnitude R. It's a little handier. It's not terribly important, but I can rewrite the generic equation as 1 over 4 e pi naught lambda. All right, and here's what it's going to do. What I'm going to do is I'm going to plug in this general quantity for r hat. All right, and so what I'm going to get is I'm going to get an r script at the. Oh, let's grab my pen. I'm going to get an r script on the top instead of r hat, and then what I'm going to get is I'm going to get an extra r on the bottom. So this now becomes r cubed dl, just a different way of writing what we had up top. All right, and then let's actually plug that in. So for our particular case, lambda's constant. Let's pull it out. And then it's going to be the integral of z hat minus x prime x hat over z squared plus x prime squared to the 3/2. Do you get that? Because r script is the square root of z squared plus x squared, and then we're cubing it. Right? We're cubing it down in the bottom here. And then that's going to be dl prime. In this case, we're going to be integrating over dx prime. And we'll review the picture to see what all this means once more. So that's it. So our final answer, and you can plug this into a computer. This one you can split up parts, but this is what we did all the work to get, and the rest is just a nasty integral in the computer. Alright, I'm going to show you, again, let's copy this over to another screen and just talk briefly about what it means, and then we'll go on to example 2 in the next screencast. So here's our final answer down here. I've added the limits and integration, and basically I just wanted to go over what this is saying. So given a little line element of charge here, what we've set up in this integral, and this is very, very cool. This vector, you can see z is going to stay the same even as our script is changing for each point. So imagine that we start from L here. We have a little line bit. We have a little bit here. Well, that R script vector is going to be like this, and it's going to have a different magnitude. Then we go the next element over, and over, and over, and over. And so what the integral is doing is keeping track of each of those vectors and how far they are from the point. Therefore, the strength one at a time as we integrate and integrate and integrate. And it's going to sum up infinitesimally each of those little vectors, which represent the bits of charge, how they're producing field. And it's all contained within here. That's it. The next step to do is to throw this into Sage or Wolfram Alpha, or if you're clever enough to do it on your calculator or know the integral. That's it.